Hello, my name is Michael Taylor. I am Director, Global Outreach and Strategic Initiatives here at the Society of Naval Architects and Marine Engineers. And I want to welcome all of you to what is our first corporate affiliate webinar coming from headquarters. And we're very happy today to have ABB, one of our corporate affiliates, starting us off with battery and hybrid electric vessels fitting the right solution. Our speaker today is Peter Bren. He is Technical Solution Manager for ABB. He's responsible for designing pure electric and hybrid diesel electric marine systems. Prior to that, Peter spent 8 years with ExxonMobil's marine affiliate, Sea River Maritime. Peter has a BS in Naval Architecture, Marine Engineering from Webb Institute, and an MS in Transportation from MIT. Peter has spent his career in the energy industry because of a concern about the dual challenges of providing affordable energy to the world while responsibly managing climate change risks. Peter has been an active citizens climate lobby volunteer since 2013. And now before I kick it over to Peter, let me just tell you how the procedure for today. We will allow time at the very end for questions. Please feel free that through any time during the presentation today to put your question in the question dialog box, just type it in. And at the appointed time, I will read them out loud and Peter will answer them. We are recording this. The recording will also be available shortly after the conclusion of the webinar. And we plan on sending a PDF of Peter's presentation to all that have registered as well at the end of the presentation. All right, without further ado, Peter, I'm going to turn it over to you.
All right, Michael, well, thank you very much. Really appreciate it and appreciate everybody on the line here today. So as was mentioned, the title for today is Battery and Hybrid Electric Vessels, Fitting the Right Solution. And just to give a little context to that title, the thought that we had was, there's certainly a lot of interest in hybrid and electric propulsion. Certainly the buzzword that's out there now, and we certainly have a lot of interest from folks. The question is, how do we make sure that we're designing these systems and talking about them in a way that adds value to the end customer, and sort of what is the value that we can expect to gain from these designs? So that's really what we want to focus on today, is that value proposition. So as was mentioned, my name is Peter Brin, Technical Solutions Manager for ABB Marine and Ports in North America. Web grad of 06 and MIT 07, and really like to thank SNAMI for this opportunity. We're excited to be the first corporate affiliate partner doing this webinar and excited to be doing this today. The agenda, first I want to just talk about some recent successes in this area. There's been a lot of activity and we'll share some of the most recent ones. As I mentioned, we'll talk about the value proposition. What is capable, what's possible with these technologies? What are the enabling technologies? We'll spend a lot of time on that. Talk a little bit about ABB and then end with some Q&A. So let's start with some recent successes and celebrate kind of what's going on in the industry right now. Some of you may have seen this recent announcement about Maid of the Mist. These, of course, are the vessels that operate in Niagara Falls, and ABB is very proud for this particular project to be the provider for this system. These will be all-electric ferries, the first of which will be introduced later this year. The vessels will have installed on board 316 kilowatt hours of batteries, energy storage, and she'll charge with about 700 kilowatts each voyage for about 7 minutes between voyages. So we understand this to be certainly among one of the first all-electric ferries in North America. We believe it to be the first one built in the U.S., so we're really excited to have that. But of course, this really follows a tradition that has been alive and well in Europe for a little while now. And another project, this is one of ours, the Vision of the Fjords, also an all-electric ferry. That's been in operation for a couple of years, similar size to the Maid of the Mist. So the technology, had been established already, and we had sort of a game plan to follow. And then on the much larger side, we're also very proud to have the 4 sea ferries, which is the, when I was going to present this, I was going to say, these are the largest all-electric ferries in the world, and they are right now, and we're very proud to have that title. And I was also going to say, but I'm looking forward to when either we or one of our competitors takes that title away from us, because there's so much activity in this space that we're waiting for the next announcement to make. And I just saw yesterday that congratulations is in order for our competitor Danfoss. They are working on a project that is going to be slightly larger, have a little bit more battery capacity than the 4C ferries, but we're very proud of this one for sure. These boats operate between Denmark and Sweden, and they've been in operation for a year or two now. And finally, looking ahead a little bit, we're also very excited to have this tugboat, which is, or push tug, river push tug in France, and this will be a fuel cell conversion. So this is very exciting, both because, as we'll discuss later in the presentation, fuel cell technology is really starting to become more real, and also because it's being used now in an industry that's particularly relevant here for the U.S., which is the workboat industry, and it's one that we focus a lot on. Now, I want to point out too, this presentation is, ABB is what I know because I work here, so it's a little bit ABB focused, but I'll certainly point out where I can, where this is not intended to be a sales pitch. It's intended to be about the technology. So we'll definitely try to point out when things apply to our competitors as well. But let's talk a little bit about give an overview of what are we talking about and sort of where are we coming from here. So, of course, the IMO has set out some ambitious goals around CO2 reduction. They're looking at 40% by 2030 and up to 70% by 2050 reduction. So to meet those ambitious goals, we need to think about doing things in a different way. The pathway that ABB sees toward getting toward a zero-emission future is starting today with where the industry is, looking at battery systems and shore charging. We'll talk about both of those technologies today. That's really sort of electrifying vessels where we can electrify them and it still makes sense. It's still, cost competitive. And so that's sort of where we are today. And we're starting to push the boundaries on fuel cell technology. In the short term, probably using methanol and LNG as a fuel, but eventually looking at moving to a pure hydrogen-based economy for, at least for heavy transportation, ocean-going vessels and whatnot. And that's an area we're focused on very much as well, as are some of our competitors. So for purposes of today's discussion, really, I'll say that electric propulsion, as we're defining it today, is really any vessel that's using electric motors to power some or all of its propulsion. That could be power takeoff and take in, diesel electric with battery and or with shore charging, battery electric vessels, fuel cell vessels, or even vessels with some renewable generation on board. All right, so what's the value proposition we're looking at? What are some of the things that we can gain by considering hybrid and electric propulsion? So I'm going to put it into 6 categories, and we're going to sort of come back to these throughout today's presentation. First, I've already mentioned it several times, reduction in fuel and emissions. But there's also opportunities to reduce maintenance costs, to improve redundancy and uptime, to improve performance on the vessel, to integrate different types of equipment more easily, and also to make it easier for the designers, the naval architects and marine engineers who are on this call, as well as the shipyards in their installation. And then the technologies that we'll specifically look at, one, we'll look at electric propulsion. We'll look at considering a DC-based power system as opposed to an AC-based power system, and we'll talk about why we might consider that. Energy storage or batteries, shore charging, and fuel cells. So let's jump right into it. So electric propulsion is simply the idea of, again, powering the vessel with electric motors, either in part or in full. And anybody who's worked with a conventional diesel-electric arrangement is familiar with the fact that one of the big benefits is you get improved redundancy and uptime. So in this particular arrangement that's shown on the screen, we have 4 diesel generators connected through a normally closed bus tie. We have an energy storage, a battery bank on board as well. to deliver some backup redundancy, and there's some benefits of that we'll talk about. But of course, you know, the benefits here are you could take any one of those engines out, or you could even take one side of the electrical bus out, and you still have at least limited power for, you know, partial, you could continue underway. This is particularly important in, you know, if you think about, again, the workboat industry, where if you have a boat going up the Mississippi River and you lose one engine, traditionally in a diesel mechanical arrangement, they'll pull that boat aside, you know, for the redundancy. They want both engines. They can operate with one engine, but they prefer to have both for a redundancy standpoint. So, you know, so you're going to have downtime. So one of the big benefits is redundancy and uptime. Of course, the other one is flexible equipment integration. You can simply plug more pieces of equipment in more easily once you have that electric propulsion. So what does electric propulsion enable? What are some of the benefits? Well, anybody who drives an electric vehicle would probably know instant torque is key. And when you look at the torque curve for a motor, as shown on the graph on the right, on the x-axis we have speed, and on the y-axis we have a few things plotted, but in green is torque. And you see that pretty much you have full torque available from 0 up to 80%, and then it's artificially limited above that for purposes of the motor integrity. But you pretty much have full torque throughout most of the power range, and that's really critical at those low speeds, low powers. The other thing that we can do is we can really improve demand and load matching. So again, I'll pull the workboat as an example. You know, and there's so many of them that operate in the U.S. and North America. A lot of these boats spend a remarkable amount of time at low power. Oftentimes, and a harbor tug is a great example of this. Oftentimes, the engines will be sized for maximum power, so, you know, maximum bollard thrust or full underway. But the reality is that the majority of the time that they operate, they're really at low power. And the example that's shown here, this is kind of a probability density function of the operating time of a fleeting boat, right? These are the boats that sort of move barges around along the Mississippi River. On the x-axis, you can see the power demand, everything from idle up to 95%, and then the y-axis is the percentage of time. So you can see here about 70% of the time, the boat really is at very low power. And if you have two large diesel engines that are idling most of the time, which is often the case, just again for that redundancy purposes, kind of awaiting commands, which may come at any moment, that's really a lot of idle time that you're we're wasting fuel and running hours. And so if you can better load match by having smaller engines through a diesel electric system, what we see is, and the graph on the right, we have 4 different cases. We have a diesel mechanical case in gray, diesel electric with battery, and diesel electric with battery and shore charging. So in each one of those cases, we're pretty much reducing the number of running hours, which of course helps from a maintenance standpoint, as well as a fuel and emissions standpoint. All right, so now we've talked about just some of the high-level benefits of considering an electrified system. Why would we consider DC grid? Why would we consider a DC-based system? I'm sure most of the folks here are familiar with AC. It's certainly the industry standard. ABB has done plenty of work with AC. It makes sense in a lot of application, but why would we consider DC? And kind of the shorthand answer is that because DC is basically the least common denominator for most pieces of equipment, and we'll talk about what that means in a second here. So on this slide, what I'd like to do is not really justify DC yet. We'll talk about why we do it in a minute, but really just describe what it looks like as compared to an AC system with which you might be familiar. So the graph that's shown here, or this, the one-line diagram that's shown here, shows a conventional AC system. We have 4 generators, 2 on each side, feeding into the AC bus with a bus tie. Of course, as those generators come online, they need to be synchronized with each other, and so you have one common synchronized bus. On the ends here, on either end, you have a transformer going off to power your hotel loads, your auxiliary loads, pumps, lights, plugs, all those kinds of things. But then in the middle here, of course, you have your dominant loads, which are your 4 propulsion motors. In this particular case, we have 3-phase transformer going to the variable frequency drive, which goes from AC to DC, then DC back to AC, and out to the motor. Okay, so that's kind of your conventional diesel electric arrangement. compared to that, what a DC grid system would look like. And again, this is common for us, and some of our competitors have similar systems. We have, again, the same 4 generators, but now we've moved the rectifier. In this case, it's actually shown local to the generator. We can also move it to within the cabinet. It's actually pretty common that we have it within the cabinet, but the way this one is shown is that the rectifier is local to the generator, which we can do that too. But regardless, it's converting the AC, so it's still an AC machine, AC generator and AC motor down here, but it's an AC machine, but you have a common bus that's DC. One of the challenges in this, traditionally with DC power distribution, is that breaking the current is much more difficult. So for fault tolerance, typically the bus tie associated with a DC system has traditionally been much larger and heavier. So one of the enabling technologies that's allowed us and a few of our competitors to start marketing these systems is the fact that we've kind of solved that problem of the bus tie and developed a cost-effective and smaller, simpler solution. So that's really a key enabling technology. But then what you have on the consumption side is, again, the same off-grid consumers here at either end. Now all of your motors have an inverter for DC to AC to get variable frequency on the motors. And of course, right here, you have a battery connection, which can either be put directly online. So sometimes you don't need this converter that's shown. In this particular case, we are showing it. It really depends on the system, whether we need that or not. But that's the basic concept. Now let's talk about why you would consider DC and what some of the benefits are. So let's first start with a conventional diesel mechanical vessel where your AC system is really just, again, powering the onboard consumers, but not propulsion. In this particular case, there really isn't any compelling reason to do DC. In fact, it probably makes more sense to do AC. So what you see here is what you'd have on most vessels that are diesel mechanical, a couple of generators connected to a switchboard, and then the consumers, and pretty simple, straightforward. Once we move, however, the electric propulsion to the electrical system, we've now moved a significant amount of power into the electrical system. And by doing that, we introduce several complexities that are more easily addressed by DC. So, pardon me. So one of the benefits with a DC system is you don't have to parallel generators. So that leads to a couple of benefits. One is that your generators we can consider doing variable speed engines, and that has significant fuel savings, and we'll talk about that in a slide in the future. And the other thing is that you can quickly bring generators online because you don't have to worry about the paralleling process, and we'll talk about some of those benefits in a minute. In addition, there's the potential to reduce footprint and weight because traditionally the way that AC systems are developed is when you have your variable frequency drives, which can be scattered around the vessel, as is shown here. The benefit to that, of course, is it's flexible. You can put them, where you need them. But the downside to that is that oftentimes those units, there's some redundancy in the cooling systems that are involved, and you also might have, you have to provide cooling to those units. Also, if those variable frequency drives are in the engine space, then, it's not a very good environment for electrical equipment. So what we do with the DC grid system is we take all of those converters, and again, usually the rectifiers, even though they're shown here with the generators, we usually move them down here into the lineup. They'll all be put together in one lineup, in one cabinet, and that cabinet can expand or shrink as needed depending on the size of the vessel. But basically, it's all in one small footprint. It can share auxiliaries, particularly like the cooling system, and can be factory tested. It can be tested at the factory and delivered to the shipyard, landed on the deck, welded down or bolted down and connected and good to go. Not to trivialize the commissioning process, but having that all in one cabinet really simplifies it quite a bit. And the third benefit is a performance one, which is that with a DC-based system, you really you significantly simplify the harmonic issue. So since you have these big consumers, these big propulsion motors that are now on a DC system, the propagation of harmonics back into that DC system really isn't a problem. And you can now and you'll have much cleaner power also for your off-grid consumers, like your pumps, your lights, your computer equipment. Once you add energy storage, so batteries, it makes even more sense to go DC because batteries, of course, are inherently a DC machine or DC piece of equipment. So tying them in is a lot easier. And then if you add shaft generators, again, getting back to that synchronizing issue, shaft generators want to turn at whatever the speed the engine's turning, of course. And so incorporating them onto the DC bus is much simpler. So the more stuff that you put onto the system, the more attractive DC becomes. So what are some of the things it enables? Now, we already talked about some of these things, but we'll dig a little deeper into them. So here on the left, of course, is shown a typical SFOC, fuel oil consumption curve or map for a typical engine. And we see a few curves of interest. So we'll start on the x-axis, we have speed. On the y-axis, we have power. And of course, in blue here, this line represents the propeller curve. And that propeller curve is typically where the engine, it might deviate a little bit, but it's generally going to follow that, or at least the engine will perform between the blue curve and the green curve up here, your maximum continuous rating, or MCR. The other curve here, the red curve, represents if you have a generator that's at fixed speed, at fixed RPM. And in that case, pretty much your fuel oil consumption is just going to be whatever it's going to be. So if you look at the table on the right, or the graph on the right, we have speed on the x-axis, or engine load, power on the x-axis, and fuel consumption on the y. And, it jumps out pretty quickly that the opportunity to pick the ideal speed for the engine at any given power load can be very attractive from a fuel standpoint. There are pretty dramatic savings available. The benefits aren't as dramatic for every engine. It varies per engine, but in this particular case, there's some big savings opportunity. The next benefit, as I mentioned, is integrating batteries. So if you're looking at integrating batteries, the appeal of DC grows pretty quickly. So a conventional AC system to integrate a battery, I won't go through the details of it, but as you can see, there are multiple conversion steps that have to happen to get that power from DC up onto the AC bus. But in a DC system, there are two different ways you can integrate a battery. In short, if your battery is, anybody who's familiar with batteries, you probably know that when a battery is fully charged, its voltage will be higher than when it's discharged, right? So if you have a typical battery system, might be 900 volts when it's charged, 700 volts when it's discharged, let's say on a typical boat project. So in order to maintain constant voltage on the bus, we would typically use a DC-DC converter as shown in this arrangement. However, if batteries are your sole or your majority source of power, it sometimes makes sense to consider doing a direct online battery and then accepting the fact that your bus voltage will vary throughout the day or throughout, as the state of charge of the battery changes. And then, so you have to design the rest of the system to accommodate that, but that's certainly possible. And it simplifies the design a little bit, makes it a little more efficient because you've got one less conversion step, and certainly reduces the amount of equipment on board and the CapEx associated. So regardless of which arrangement, the DC grid opportunity for integrating energy storage is much easier, whichever option is chosen. The other thing is that DC grid can improve safety and performance. So one of the key things I mentioned before is paralleling generators. So you're probably familiar that an AC system, it can take upwards of a minute to get all your generators online on some vessels. Largely because of the paralleling. With a DC system, that's no longer an issue. You don't have to parallel generators. You can just put them right online once the voltage is where it needs to be. So on this particular vessel example that we're showing here, first generator was online in 12 seconds, and all generators were online 1 second later, within 13 seconds from blackout. So that really changes, and we'll talk in a minute about one of the benefits here, that really can change the whole paradigm of operation for the operator. In addition, once you are underway, once you are operating, the ramp speed for the engines to react to changes in power demand has also been shown to be quite a bit faster. But one case study that was really interesting about this, and frankly was a surprise to us, but a really good news story, was that this fault tolerance really inspires confidence in the operator. So the vessel shown there is the NKT Victoria. This was a cable layer that was an ABB project, and we estimated that the owner would save about 10 to 15% on fuel just based on having variable speed engines. So the vessel was built, put into service. About a year later, we went back to the owner and said, hey, we thought you guys are going to save about 10 to 15% fuel based on our calculations. How are we doing? And they said, well, actually, no, we're saving a lot more than that. We're saving upwards of about 50%, 50. And we said, how is that possible? That's not, how is that possible? And they said, well, I think, basically what we concluded was the reason was the way that they operate the vessel. They had so much confidence in the ability to recover from a blackout situation that the normal operation showed that you'd normally have, 2 engines online for redundancy purposes and, at all times. And so, when they're under operation, which typically doesn't require a lot of power, but, requires some power, they would have these 2 big engines on, but instead they were operating with just 1 engine. It was just a port generator. So it was a smaller engine that could be better load matched to the demand. And they only had 1 on. And they said, yeah, if we lose power, if it trips offline for some reason, it's fine. We can get back on in 12 seconds. It's not a problem. So they were just the whole paradigm shift of how to operate the vessel really led to the biggest savings. And that wasn't even planned. So that was a really good news story. But it's helped us to kind of think in the future about some of the savings opportunities for other projects as well. As I mentioned before, also the DC grid, the way that we tend to build the cabinets, and this can be done with AC as well, but with the DC system, we're a lot more focused on it, really bringing everything together in one cabinet. And so the single line drawing on the right is kind of a typical arrangement where we would have, multiple energy sources, potentially multiple consumers. And within this dotted line, dashed line in the middle is our DC grid cabinet setup. And of course, you can see all the converters and the inverters are in there. And again, it's built in a way as shown on the left. It's all, expandable or the cabinet can shrink. And of course, we can split it in 2 or multiple parts for arrangement purposes, connecting it with bus ducts. So from a design and installation standpoint, it kind of simplifies things. Okay, let's talk energy storage a little bit. Let's talk batteries. So the first thing I'd like to point out is I would argue that we are sort of at the leading but not the bleeding edge on batteries. There are certainly a number of reference projects out there. These ones here are within the ABB portfolio. On this slide, we see sort of an industry-wide perspective. There's many other companies working on this as well, in addition to us. And I think this slide is actually, this is actually a year or 2 old now. But looking out into the future, out to 2022, and of course, more projects have since closed since then. So I don't expect a leveling off. That's just based on the number of projects that are known at the given time. We see in green the number of vessels in operation, and blue under construction. So there's been a dramatic growth over the past 5 to 10 years of vessels in this employing the batteries in some way. So what does energy storage enable? So again, there's a lot of interest and excitement around batteries, but there are many different ways that they can be used. So let's take a few minutes here to look at the different ways that batteries can actually add value to the vessel operation. So the first is spinning reserve. So if we think back to our NKT Victoria case study I mentioned a minute ago, the idea of being able to not have to run engines, particularly multiple engines for redundancy purposes, and keep them at low load or idle during periods of low power demand, that can be a huge fuel savings right there. So typically that's done, again, just to have for emergency purposes or to quickly respond when the vessel's in standby mode. But if you have batteries, first of all, batteries respond faster than any diesel can. And second of all, you don't necessarily need a big battery bank to make that happen. Batteries can respond quickly, and then you can transfer over to diesel generator power afterward if necessary. So there's a huge opportunity just to save time when vessels are at low load, in particular for the spinning reserve opportunity. The next is peak shaving. So the idea here is that if, let's take the tug example again. A harbor tug might need, let's say, 3,000 horsepower to get maximum bollard push. But they say, you know what, we're just going to install 2,400 horsepower, and we'll let batteries give us that extra 600 horse the 3 or 4% of the time that we operate that we actually need all that power. So you can undersize your engines and rely on the batteries to take to give you that additional boost when you need it. But take advantage of the fuel savings and the maintenance savings by running those engines for fewer hours at all the other times, and running smaller engines potentially. The third is enhanced dynamic performance. So the idea here is, diesel engines can certainly respond when you need them. They'll ramp up, and they ramp up relatively quickly, but they don't like to. Diesel engines like to, they like smooth, slow changes, increases in power demand and decreases in power demand. So, when they're asked to ramp up very quickly or ramp down very quickly, you'll have visible emissions. The engine won't operate as efficiently as usual, and it could dirty your cylinders and things like that. So, to allow the battery to take those quick swings in power demand and to let the generators just kind of keep operating at a relatively constant power and then slowly ramp up at the speed that they would most prefer, that really offers a lot of benefit to the efficiency and the maintenance profile of the engine, and also delivers much better performance for the operator because you get much faster response times on the vessel. Strategic loading, this is interesting. So we already gained some benefit with a DC grid system with variable speed engines, but it's still the case that you might have a more attractive fuel consumption profile, let's say at 85% MCR, as opposed to say 50% MCR on the engine. So if you want to take advantage of the fact that you have a more attractive fuel consumption profile at a higher power, you can use the batteries to say, I'm going to operate my generator for a while at high power. I only need 50% right now, but let's operate at 85. Charge up the batteries and use those batteries, and then shut the engine off and use those batteries when we need them, and bring the engine back online when it's time to charge the batteries back up. So strategic loading can really help to determine how you load the engines, and the power management system, of course, that'll all be built into the power management system to do that for the operator, so they don't have to think about it. And finally, the ultimate goal is zero emission operation, and that can be achieved. There's a couple of ways that we can do that here. First is what we call a zero emission port stay, where you might charge up batteries while you're underway at sea, and then when you get to port, you can shut the engines off and just operate, so that there aren't any local emissions being generated off batteries. Or you can go truly zero emissions and power a vessel entirely, or in part at least, with shore power, and charge up the vessel and operate purely off the batteries for some period of time. So let's dig a little bit deeper into the technology and talk about some of the key things to be aware of. So there are several chemistries that are available, but broadly speaking, just the thing to keep in mind is batteries generally come in two main flavors. One is what I'd call a power battery. The other is an energy battery. So if we look at the graph on the right, you see several different chemistry technologies. On the x-axis is specific energy, so that's energy per unit mass. On the y-axis, we have power per unit mass, specific power. So basically, the batteries that are higher up mean you can get more power out of them. The ones on the right means you get more energy out of them for the same weight. And so most of the projects we focus on tend to be high energy batteries. We're trying to get as much energy on board as possible. But if you just want a small bank that can quickly respond, when needed, then you might look at a power battery application. Currently, the technologies pretty much all fall within the lithium-ion portfolio. Well, that's not entirely true. There are some benefits to some other battery chemistries as well that some manufacturers are working on, but most of the ones we look at are lithium-ion. So what does the battery system look like? So the components are, we'll build it up from the cell level all the way to the full system here. So a cell, most of the batteries that are in the marine market today, not all, but most are built with a pouch cell. Kind of looks like a big FedEx envelope. It'll be plastic covered, and basically inside is the anode and cathode. And that's basically the very basic building block of your whole battery system. These might be mass produced by companies like Samsung or LG Chem, or in some cases, some of the marine battery manufacturers make their own cells. But regardless, this basically forms the very basic foundation of the battery. Once those are stacked together in what's called a module, that becomes what I'd call the basic marine building block, meaning that this is now the sort of the lowest voltage increment that you can size your system. So in this example, we're saying 45 volts. But the module is really critical because the module is what's built by the battery manufacturer. It will have integrated into it the battery management system components that are needed. It will have integrated the cooling system components, and thermal management on batteries is really critical both to the safety and longevity of the battery. So they'll have these series connected cells that form the module, and then once you stack the modules together, you'll put them into a string, or also known as a rack or a pack. The string basically defines the vessel's system voltage, right? So in this example, we're saying that we're going to put 20 of these 45 volt batteries in series and get 900 volts total on our system. So that basically is, and that becomes then the smallest building block of energy that you can add to the vessel, because you need to add them in increments of 900 volts apiece. And finally, you'll stack up a number of those strings together into a bank or array, and that basically defines the amount of energy that you have on the vessel total in terms of battery storage. So everything from the cell up to the bank level will be, that'll all be integrated and provided by the battery producer. I won't get into deep discussion on this slide. Just suffice it to say that battery sizing is not as obvious as it might first seem when it meets the eye. You might look at a project and say, okay, I have a ferry. She crosses back and forth. I need 300 kilowatt hours, to get across. And so therefore I need a 300 kilowatt hour battery. Not exactly. There are a lot of factors that come into play, most significantly the number of cycles, the life of the battery, but also the power demand on the battery. So like, what is the highest power that we're going to need from the battery, and some other factors. So in short, what you effectively end up doing is it would appear you're oversizing the battery or the amount of energy that you need, depending. Probably the biggest factor is the number of cycles. So for example, if you have one cycle per day, meaning you do one charge per day, you would size a battery typically for 10-year life, and you'd say, okay, well, 10 years, one cycle a day, that's 3,600 cycles. If that's the case, you would probably use about 80% of the battery every time you charge up and discharge. That's not a high cycle life, so you can use most of the battery. If, however, you have, let's say, 10 cycles per day, so not 3,600, but 36,000 cycles over the lifetime, then you might only end up using about 30% of the battery capacity per day, give or take. This depends on the battery type, it depends on the battery chemistry, it depends on a lot of things, but broadly speaking, just keep in mind the fact that the number of cycles that you have, if you increase it, generally the bigger the battery is going to be. Typically, this is something, we and many of our competitors can do kind of an initial battery sizing for you, but ultimately we let the battery manufacturer who, is going to warranty that battery dictate the size for that application. Okay, let's talk about shore charging. So shore charging, of course, is what's necessary to charge up batteries if you want to bring that power on board. One of the benefits, of course, is that electrons tend to be cheaper than hydrocarbons, cheaper and cleaner. So if you want to reduce your emissions, that's one benefit. Also, they tend to be more cost effective. And so, we would consider doing shore charging in many projects. Some of the key things to keep in mind when you're trying to identify a shore charging system. And one thing I will say is that shore charging, being new to this industry, I've been at ABB now for about 7 months. Shore charging is a lot less trivial than may first meet the eye. You think, oh, I'm just going to plug it in, right? Well, it actually can be a lot more complicated than that. Some of the key reasons that complicate things, one is charge time. A lot of vessels don't have a lot of time to charge. They have a quick turnaround. They don't make money when they're in port, so they want to charge up quick and get out. Depending on how much energy is required, that could lead to some pretty high power that's needed to charge the vessel up. You can also have very limited space quayside and on board, so space and arrangements are a key consideration on some boats. Whether you're going to have an automated or a manual solution can be really critical. And what's the power grid capacity? You might need a really high power grid might not be prepared to give it to you. So I'm not going to go through these specific solutions, but I just want to kind of group them in a few categories. So if we look at kind of what I call the first generation of shore charging solutions, particularly in Norway, we see some very high power, i.e. greater than 5 megawatt applications. These are all automated kind of robotic systems. So the vessel comes in, the shore charge connection is made, you deliver a lot of power very quickly, the disconnect is automatic and the vessel goes away. These are all pretty much ferry applications. But in more recent times, we've seen a need to have a bow charging for ferries because there's a lot of double-ended ferries and side charging is often not an option. Sometimes there's not even a dock quayside to put the equipment on. So we're seeing some bow application, bow charging. Those are also automated, by the way. These solutions are not automated. These solutions are manual solutions. They tend to be a little lower power, 3 to 4 megawatts max, but all the way down to, you know, in the hundreds of kilowatt range. They can be sized for, and, you know, they're as simple as shown. They're really just kind of a crane style solution where the plugs land down and then the crew mates them up to the plug. And finally, you have just simple electric vehicle style chargers that can be used. The one on the right, for example, would be something used, traditionally used for buses. They're called opportunity chargers. The bus pulls up to a bus stop. This charger comes down, gives it a quick punch of energy, and the bus moves on. That could be very applicable, for example, for a water taxi application, and we're talking to some owners about that. So that's a quick overview on shore charging. And the last thing we'll touch on are fuel cells. Now, fuel cells have always been the technology that's 10 years away, right? So, but we're starting to see some more and more evidence that might actually be true this time. We're actually starting to see some real world applications. So for those of you not familiar with a fuel cell, basically it's a battery that runs on hydrogen. You can kind of think of it that way. So in this application or in this drawing, the hydrogen comes in from the left as H2. The molecule splits apart. You have the electron that goes up and powers the load. The hydrogen ion then passes through the membrane. It meets up with the electron and some oxygen on the other side, and the only output you really have is water. So it is kind of the ideal zero emissions energy source. But the challenge really has always been, where do you get the hydrogen? And we'll talk about that in a minute. But the exciting part is that there's actually quite a bit of activity out there. So in the marine space, it's still relatively new. We have about 10 pilot installations that we know of. But in the forklift space, there's about 20,000 forklifts, up to 3,000 buses using fuel cells. And Toyota's made a big investment in fuel cells. They have over 10,000 cars out there. Stationary applications, we see power grid, telecommunication, backup systems, a lot of households in Japan that are using fuel cells, and a big fuel cell park in Korea. So again, we have a long way to go with this technology, but it really is coming. And what we see in the marine space is that most of the interest so far has been primarily amongst passenger and cruise vessels for obvious reasons. But we're also starting to see some interest among research vessels and LNG in particular, because natural gas is a fuel that can be indirectly used to power a fuel cell. We'll talk about that in a second. Here are some of the demonstration projects that are out there. A few of these are ABB, a number of them aren't, so it's exciting to see that we and others are getting into this space. And within our portfolio, we're partnering with a lot of different organizations, as shown, both on the research side and prototype side. We have this project. This is a research vessel in Finland that has a 165 kilowatt fuel cell. We partnered with U.S. Coast Guard to deliver this containerized solution with Hydrogenics. And most recently, we're really excited about this delivery. It'll be a 100 kilowatt fuel cell on a Royal Caribbean ship. The fuel cell is being delivered by Ballard, and of course, we're doing the electrical integration to have it work with the system. Obviously, you know, relative to the ship power, it's quite small. It's just, again, this is really for a testing platform, and we'll look at larger units in the future. So what do fuel cells enable? So it has multiple opportunities and challenges to keep in mind. So One big opportunity is that the costs really are coming down, and they're reaching parity with diesel engines on a $1 per kilowatt installed basis. So they're actually not that much more expensive to install the fuel cell itself on a vessel. Of course, zero emissions is the key thing that makes it attractive. It also has high energy efficiency, which is another thing that makes it attractive. And it also has a comparable footprint and weight to a diesel engine. So it's unlike batteries that tend to be much larger, take up a lot more space for the same power delivered, the footprint of a fuel cell can be very compact. And also, it's lighter than diesel. For the same amount of energy delivered, hydrogen is actually lighter than diesel fuel. The challenge, though, is where do we get that hydrogen and how do we store it? So even though it's lighter, it's a very small molecule, which makes it difficult to store. And it also has a lower specific volume. So while it's lighter, it takes up more space. So it's not an insurmountable amount. It's, it can be designed in, but it is a consideration. So we talked a little bit about efficiency. Of course, for a combustion engine, we see the line in gray where, typically at lower loads, the combustion engine becomes less efficient. Fuel cells actually become more efficient at lower loads, but they maintain pretty good efficiency down to about 30%. Typically, we would pair, even looking out into the future, if an ocean-going vessel, once we start putting fuel cells on powering ships, we're still probably going to have a battery system on board, a small battery system, both to handle these low loads when they occur, and also because fuel cells, like a diesel engine, really like to operate at kind of a constant output, power output. So we would have the battery system to kind of handle those swings in the same way that we use battery systems with diesel engines. So there's definitely a future for batteries, even in a fuel cell powered world. It's certainly not one or the other. It's really working together, those technologies. The key thing, though, are the fuels available, right? So hydrogen is kind of the ideal fuel. That's will have no CO2, but obviously where we get it, how we produce it, all of those questions exist. So in the near term, as we get this technology out there, we're really looking at methanol, which of course is liquid at standard temperature and pressure, and methane in the form of LNG or compressed natural gas. Both of those, of course, still release CO2, but the overall kind of well-to-wheels process or well-to-propeller process is can be more efficient with a fuel cell because of the fuel cell efficiency, and it helps to get the technology out there so that we can do more testing. But there are containment systems available, and compressed hydrogen storage, I mean, it's certainly possible. The system on the left shows that, liquefied H2 in the middle, that's system by man. And on the right, that's a reformation system, which can take either methanol or methane and convert it to H2, and it just releases the CO2 to the atmosphere. Of course, that's not a long-term solution, but for now, that's an important component. The way that we kind of see the market right now is there are a lot of off-the-shelf units in the smaller power range, couple hundred kilowatts. But we are partnering with Ballard at the moment on a 3 megawatt unit for marine use, and that would really be targeted for ultimately ocean-going vessels. And so I know we're getting a little tight on time here, but just in quick summary, I think we covered a lot of different value propositions as well as several different technologies. And I won't go through all this slide, but it'll be in the reference that you can look at afterward. But we've seen benefits on fuel and emissions, on maintenance, potential opportunities for redundancy and uptime, improved performance, particularly with electric motors, flexible equipment integration, especially with the DC grid system, and opportunities to simplify the design and integration of equipment for naval arcs and marine engineers. So quickly about ABB, if you don't know us, we're basically a large industrial electrical equipment integration company. Our Marine and Ports division has offices all around the world. We're very well known. If you don't know us, you might know us from our Azipod product line. This is very common in the cruise industry, also in offshore oil and gas, and in ice-breaking vessels. The units are down from 1.5 megawatts all the way up to 22. So I didn't really talk much about this today because it wasn't really the focus, but this is a pretty big part of our product line in marine. And here in North America, we're hubbed in Miramar, Florida, and Houston. And with that, I think we can open it up for questions in the time we have left. Please do come see us next week at IMX in St. Louis, and we'll be at the SNAMI convention in Tacoma later this year. So thanks very much.
Well, thank you very much, Peter, for what I considered a very comprehensive and informative presentation. I did mention in the chat field, type in any questions that you might have, and I'll be happy to read those out for Peter's benefit, and we can get it onto the recording. But since there's not any in the box to begin with, I guess I'm going to take the moderator privilege and ask a question, if I may. I particularly enjoyed, as we discussed before we got on the call, got some background in the energy area and renewables and all of that. And I was very struck by your fuel cell and your battery portions of your presentation. And in particular you mentioned, the fuel cells was kind of the area where we've been waiting for the enabling technology, the key technology. And I think it's interesting to see that the cost parity is getting close to diesel, and you see more and more applications out there. That's very promising. But going back to the battery, in your slide, you drew the distinction that ABB is on the leading but not the bleeding edge. And I guess I'm kind of curious, what sort of, bleeding edge, or what are the most, what are the really enabling technologies that you see out there to sort of transform what we get from batteries? Because that's been the expectancy that, you see all this technological innovation at a breakneck pace, but batteries lagging behind. I'm just curious what you see out there to sort of transform batteries and get batteries caught up with all of, sort of the other breakthroughs.
Yeah, great question. I mean, I think, the reality is marine, and I think this is true and has been true for a long time. Marine is generally a low volume, business. And so, if you look at the electrical vehicle or just the auto industry, it's design one, build 500,000. Marine, it's design one, hopefully build two, maybe five, So scalability has never been something that, and for good reasons. I mean, that's not a criticism. It's just the reality of our industry. So, optimizing batteries for the marine space is certainly a challenge because, the scalability, every project is at least somewhat unique. The benefit is that we're kind of riding the wave of, electrification at large, and really the auto industry, I think, is, pushing this and bringing those costs down, and really opening up the door for marine, for stationary sources, et cetera, and other industries that want to ride that wave. So not to say that we necessarily use the same batteries. The batteries, for example, that a Tesla uses are great for an EV, but not for necessarily a marine application. We have a lot more cycles than a car would typically have, so we wouldn't get the longevity. So it's not necessarily that we use the same equipment, but we can leverage the benefits of, a lithium supply chain, of the technology that's being, found there. So I think we're really, as far as battery development, there's some great companies working on batteries for a marine application and figuring out the aspects that are needed to marinize batteries, like particularly the thermal management system. And working on developing and following class requirements and Coast Guard requirements, et cetera. But I think really the biggest enabler for us is going to be the continued growth of electric vehicles.
All right, thank you very much, Peter. Okay, so I've got some questions here. Let me read the first one off. How does size and weight of some of the systems that you've discussed today stack up to a conventional system?
Yeah, great question. Let me see. I'll break the answer into two parts. First, let's talk about just the base equipment, meaning the switchboard, the conversion gear, the motors, the generators. As compared to a conventional system, it's comparable. You know, it's a little bit different. You with motors, the nice thing is you have a little more flexibility in where you put them. Same with generators, you can move your engines, so it's a little more flexible for the naval arts. So you put them wherever you want. For the and same with the switch gear, you know, you can put that in the you put the DC grid, for example, in the ECR or in an electrical room. So that's pretty comparable. If you look at batteries, that's where it can range pretty dramatically. So if you have a relatively small bank, it's you know, just for say like a peak shaving application, you could easily absorb that. If you're going to move to an all-electric vessel, you'll have to give some thought to, you know, how much weight you can afford to spend. Now, having said that, what's very interesting is, you know, most vessels, of course, are built with bunker capacity for, you know, because you don't want to bunker every voyage. So, you know, you'll have a lot of bunkers on board, and you can operate for, you know, sometimes weeks at a time between bunkerings. With batteries, because the capacity is, you know, the weight is a lot higher, you usually just put enough energy on board for, you know, one back and forth voyage, you do quick shore charge, and you get back underway. So even though diesel is much more energy dense than a battery, typically, if you look at the systems we put on board and compare it to the amount of fuel that's usually available, it's actually not that much different either. In fact, I've cited some systems where I think it's a little bit lighter than the amount of bunkers you have. So it is a consideration. It's something that needs to be thought about carefully, but it's definitely possible to have a very comparable weight and footprint on a lot of these vessels.
Okay, thank you, Peter. Next question, what's your take on batteries and fuel cells working together?
Yeah, so like I said, we talked about that a little bit earlier. I think in the near term, you know, batteries are, we're basically trying to deploy them where we can because you can get them off the shelf. The costs are such that you know, typically a battery vessel means higher CapEx, but potentially much lower OpEx. So, you know, where that proposition is attractive, we can offer those systems. Fuel cells, at least at the moment, are more of a, it's going to be a more involved process, right? Because it's still a new technology, and we'd be very excited to have a fuel cell project here in North America. We'd love to. So if anybody on the line is interested, we'd love to talk to you about it. And there's definitely application for it, but at the moment we don't have anything active in North America. But again, I think longer term, I do think that there's, you know, if you envision 15 or 20 years from now, container ships that are running on fuel cells, I do expect that there would be a modest battery bank on board to, again, allow for those transient loads and fluctuations in power, and also maybe to help improve the efficiency at low power when the fuel cell efficiency drops off. Okay.
What do you see as the key enabler for the multi-megawatt applications?
That is well, again, it probably come back to the fuel cell. And I don't, to be honest, I'm not as intimately familiar with fuel cell technology to be able to give a really good technical answer to that question. But I do think it's fair to say that when it comes to fuel cell technology, the technology of the cell itself is, I think, less of a question than the question of where do we get our hydrogen, how do we produce it sustainably, and how do we store it? I think those are the bigger challenges that need to be looked at. So I don't have a great answer for that question, but I think broadly speaking, that would be the biggest challenge that I think I see.
Okay, let's try to squeeze this one. We're right at the end here. What is a typical payback period for a battery hybrid system for a workboat application, considering the cost of the installation of all the electrical components versus the efficiency savings gained?
Yeah, that's a really good question. And like any good engineer, I'm going to say it depends. I mean, on the pot. So we've been working to answer this question a lot internally because, you know, every operation is different. The operation of a fleeting boat in the inland river looks a lot different than a line haul boat, looks a lot different than a harbor tug, et cetera. So it can vary a lot. I mean, it can vary between, on the most attractive end, we've seen 3 to 5 years. On the least attractive end, we wouldn't even bother talking to the customer about it because it's too far off. So, I mean, it can be that good, or it can be, you know, less attractive. There might be other reasons why an owner wants to consider it still. But, you know, again, there's different, we can do a pure battery operation where you can save a lot of money because, again, electrons tend to be cheaper than hydrocarbons. Or we can just put a small battery bank on board to optimize the system and get, you know, a big benefit with a small price. So it really depends on the operation, but we'd be happy to help folks try to answer that question for their particular application.
All right. Once again, thank you, Peter. We're right at time. There are more questions. I know Peter, as we discussed prior to the webinar, you can see his contact, his email there, and you know, Peter's happy for you to reach out to him directly with your questions that you may have had that didn't get answered. Shortly after we complete today's webinar, the recording will be available, and we're going to send a PDF version of the presentation today to everyone who registered for today's webinar. And let me just close it off by saying thank you so much, Peter and ABB, for being our very first corporate affiliate webinar here at SNAME. I think it was a very successful start, and hopefully we can keep that success going forward. And thank all of you for attending today.
Yeah, thank you, Mike, and thanks everybody for being here. So excited to see such a great turnout. Really appreciate it.
All right, signing off. Thanks again.